So, hi everyone. Very good morning. I hope all of you are well and happy today. Yeah. So let's start. So today I just came up with this memoization technique, how to increase your particular performance and even uh, decrease the time complexity. So for Fibonacci series using the recursion in Java as well. So as you can see on my screen, there is a diagram that I clearly mentioned on over here. So what is happening here? Yeah, as you can see, here is a box Fibonacci. There we are computing the logic over here. So this is method actually. This is method. This is method, and inside that method we are computing the logic. So I already explained this logic to you all. So the same thing is happening over here. But what is happening? We are using the cache technique. Okay. So we are using the cache technique. So you using those cache technique, what we are doing. So in my second diagram, as I am just opening the second diagram, what is happening? If you see, yesterday I explained the Fibonacci series using this Fibonacci simple tree. Like if there are we want to find the series for three, right? Fibonacci. So it will be simply like that: three. Then it will be divided into part two and one. So this is nothing n minus one and n minus two. Again, it is divided n minus one and minus two. So you can see here. You can see here as well. Let me zoom it. You can see here f1 and f1. So it is duplicate process is going to be happen here. So for removing this duplicate nodes, and we use these nodes, if one time that node is already processed, so we store the result for that nodes inside somewhere in cache to increase the performance as well as decrease the time. Okay. So that's what for this approach we are using the memoization technique. So here the every node will process only the single time. So for this what we are using the cache over here. Okay. So that's what, and we are checking the cache technique doesn't equal to zero. So let me explain this. How we are doing that. So what the program is same as I created yesterday. The program is same actually, but if you see, I added this cache. I added this cache. Okay, so this is a cache is nothing, it's a array. It's a array which we decided some size over there according to the number of nodes, right? So what we are doing, what we are going to use for this cache, we are going to store the result of the node that is going to process. Okay, so in second time, if that node is coming as a input, so what will happen? It will look inside the cache first. Then, if that node is exist there, that node result is exist there, it will get that result and use that. But and it will not process that node again. But if it is not there, then it will process, right? So that's what happening inside this code currently. So if you see, I am calling this method Fibonacci. So Fibonacci is it is same using the Java. I just created this, and this is your base condition. Base condition is main important. Okay, so you have to your base condition should be uh, very strong or very, you know, that if your base condition is failing, your program is going to be crash in some other conditions as well. You have to check all the scenario in that case. So what our base condition, if n is less than or equal to 2, so return n. And the second base condition is, if the second medium condition, if that result is already available inside the cache, is already available inside the cache, then we simply return that result only. Okay, so here we are the using the logic. So previously we were using the a plus b, as you remembered c is equal to a plus b. So here, and where a is equal to, and just a have some value and b have some value, but that value should be following the architecture n minus 1 and minus 2, right? So here we are calling these particular methods using the n minus 1. So here this particular node, these are this particular node. So as you can see, this is the root node. This is the Fibonacci method is a root node with the int n fib cache, and this is particular n minus 1, that is n minus 1. Suppose that n is 5, so n is 5, that is going to be broken inside n is 4 and n is 3. Perfect. Okay, so first it will call the first this method will call. Suppose that n4 is calling, right? If n4 is calling, then it will go there and check n is greater than n is less than 2. No, it will not go inside. N is available inside this. No, it will not go. So it will come here, and the value is still inside the particular stack memory. So and it is again go for this n minus 2. N minus 2, 5 minus 2 is equal to 3. So 3 is less than 2. No. 3 is available inside the cache. No. So it also going to store inside stack memory. Okay, stack or particular. So what is happening here? If you see what is happening here, again that particular 4 is breaking inside the 3 and 2. Okay, 3 and 2, so it will go for 3 and it will go again for 2. Okay, at this particular 5 minus 2, 3, 2 and 1, it will break. So if suppose that if n is equal to 2, so it simply it will return this. So this method will return this. Okay, return 2, and if n is less than 2, n is equal to 1, so this method will return again 1. Okay, yes. So that's what we are applying here. So we can clearly see inside the diagram, this is something. So what is happening, f3 is breaking in f2 and f1. F2 is 0. Okay, breaking, but for f1 we use again this result from the cache. So that's what happening here with the Fibonacci using the memoization technique. So memoization thing, here we are remembering those things. Okay, here we are here we are checking that is that is existing inside the cache or not, and here we are remembering whenever the function is returning anything, then it is going to store inside that. That's what currently is happening. Okay, so if you want to check, we can debug this program as well. Okay, already debugger is there. So let's enter the file over here. So go there, and I am calculating the time as well, you know. So I will compare this time in last for the recursion, recursion using the Fibonacci and memoization technique. Okay, so this loop is going to actually execute. So here in debug mode I am running, so maybe the time complexity can be increased because debug in runs slow. Okay, so I yep, now n is equal to 1. So as you can see, 0 1 already printed because 0 1 I just given as a base condition, and in as a not base, sorry, 0 1 it is the starting always we print. Okay, in Fibonacci, so that I printed, so we are not going to process it or checking the condition for that. So I am starting it or simply from 1 just loop. Okay, so this is RC dot Fibonacci we are calling over here with the I is equal to 1 and fib cache. Here we are also sending this cache over there. So if you see n is equal to 1, I 1, n is equal to 1. So what is happened? 1 is less than equal to 2. Definitely this condition is going to be true. So it is going to be true. So it is returning here n is equal to 1. Okay, so it will print that particular. If you see, it is printed here n is equal to 1. Now it will go for the 2. Okay, so it will go for the 2. So here n is equal to 2. 2 is less than equal to 2. Condition will met, it is true. So return it will return 2 simply. So it will print here 0 1 1 2. So here printed the 2. Okay, so now it will go for the 3. So let's see. So it is going 3 here as well, n is equal to 3. So check that particular n is 3 or not. Yeah, this condition fail here. Now it is going and checking inside the fifth cache. So we can see here inside the side by side is there on the 3, 0 is available. So this condition is also not going to met. Okay, so it will not go inside, it will come here again. Fibonacci n minus 1, n minus 1 here, n is equal to 3. So 3 will be breaking inside, 3 minus 1 2, and 3 minus 2 1. So there are two child will create, one for 2, one for 1, for the 3 as a root. Okay, perfect. So if you see the first child, it is going there, n is equal to 2. 2 is less than equal to 2, perfect. So it will return the 2. Okay, it will return the 2, but it will return for this, it will return for this 2. So here we have the 2. Now now it will go for the 1. So it is going for the 1. The second child it is calling, so 1 is less than equal to 2, it's also true, perfect. So now it is, so here if you see, previously 2 plus 1, so 3. Okay, so 3 will store, yeah, 3 has stored. If you see here the returning value is 2, here the returning value was 1. So 2 plus 1 is equal to 3, so 3 is stored. So 3 is stored in the fifth cache. If you see on the third index, 3 is stored. Okay, now let's go there. I is equal to 3 is completed. Now we are going to for I is equal to 4. Okay, so here n is equal to 4 is there. I is nothing. I is indexing, that is in assigning as a parameter inside the Fibonacci. So where the I value is equal to n for Fibonacci, right? So don't be confused here. So here you can see n is equal to 4, because we ith index is passing as a 4 here. From here 4 we are passing. So here n value assigned as a 4. So 4 is less than equal to 2? No, definitely no. So let's go there. Let's check on the fourth. Is there any value is there? No, it is equal to 0. So this condition also false. It will go there. Now what is happening here? 4 minus 1 3, 4 minus 2 2. So there are two child, 3 and 2. So first, which one will process first? I think so 3. So let's see. So now it's going for the 3. 3 is less than equal to 2? No. Okay, 3 is yeah, 3 having the value, so it will go inside, definitely it will go inside the cache and it will return that cache. So now it will return, this particular will return the 3 as output. Now what is this? 4 minus 2, now it will again call for the 2 here. Now 2 is less than equal to 2, perfect. So return, so it will return 2 here. So previously written the 3, then return 2, so it will for the 5 now. So 3 plus 2 5, so 5 will store, as you can see. Sorry, I was wrong. Yeah, 5 store here. For the fourth one, 5 has stored, because it returned the 3 and it returned the 2. Okay, so 5 will store here, if you can see, in the fifth cache, on the fourth index of fifth cache. Okay, so let's, now it will go again and come for the n is equal to, now it is going for the I is equal to 5, because I has increased from the 4. Okay, so it is the last index. So it will go for the I is equal to 5. Now n is equal to assigned as a 5, because I is coming as 5. So 5 is less than equal to 2? No. So here we go inside the fifth cache and checking for the 5. Is any value is available? Nothing. It is equal to 0. So the condition is false here. So now it will go again. Now check. The two child has created for the 5. 5 minus 1 and 5 minus 2. 5 minus 1 is 4. 5 minus 2 is 3. Okay, so first it is going for the processing for the 4, then it's processed for the 3. So let's see. 4 is less than equal to 2, perfect. 4 is less than equal to 2, perfect. It will not go inside this. Okay, so it is false. Fifth cache n is 4. Fourth index having any value? Yes, so it will return that. It is written 5 here. So 5 is returned here. And now for it will go out the second child. Again the compiler go for the second child, that is 5 minus 2 3. Okay, so n is equal to 3. Definitely this condition is not true. 3 is less than equal to 2. So 3 never less than equal to 2. So this is not true, it will not go inside. Okay, now go there. Okay, on this fifth cache is having any it is checking fifth cache 3 index having any value? Yes, if you can see fifth cache. Okay, So fifth cache having the three on the three index three value, so it will return the three. Okay, it will return the 3. So here we have the total count here, 5 plus 3, because fourth return the 5, third return the 3, third index, to 5 plus 3 is equal to 8, so 8 will return. So here it will print the 8. If you see, yeah, 8 is printed. Now now n is equal to 5, so I is less than equal to 5, so I is 5, 5 is less than equal to 5, so this is the last index. And if I plus plus will happen, then this condition will false and it will not go inside this loop and it will come outside. Yeah, it came outside, as you can see. So we are just closing this. Okay, it came outside, so it is your output. It is your output. And total time millisecond is taking too much here, because we were running in debug mode. Okay, so now we are going to run this program as simple. Okay, so simply without in debug mode, how many times it is taking for this? Okay, so let's enter the 5, and it is taking 1 millisecond only. Perfect, 1 millisecond only. And again run this, and let's run for the 50. Suppose that 50, I am not entering 5, now I am entering the 50. How much time it is? Only 3 millisecond it is taking, with using the memoization technique, as you can see. And for recursion simple, without memoization technique, if I run this program, so check that how many times it is taking. For 50, same. So it is taking 11 milliseconds. It's too much. Where is 3 millisecond and it is 11 milliseconds? Okay, so it is 11 millisecond, and this was with the memoization technique, it was 3 millisecond. So remember that how much it is faster. It is faster 8 milliseconds. The same 50, for the 50 it is printing take memoization technique using, it is taking only 3 millisecond, and the without memoization technique simple approach, it is taking 11 milliseconds. So that's what. So and now let's talk about the time complexity. So how we are calculating the time complexity, I already written this. So as we know, we are breaking those particular nodes in tn minus 1, tn minus 2. So tn minus 2, so here what we are doing, we are storing tn minus 2, we are storing each node in cache, so we process node only one time. So what is happening, if tn minus 2, suppose that tn minus 2 is inside the cache, and again the tn minus 2 we are going to process. Okay, so first we are going to checking inside the cache, so the your time complexity will be, we go one is there. So what we are returning here, tn is equal to tn minus 1 plus 1. Now the same, tn minus 2 again tn minus 2 plus 2. Okay, it will increase again and again, tn minus 3 plus 3, because that particular node we already processed. So so on, tn minus n plus n, so the complexity will be b go n. Okay, so this is too much less. And for the simple recursion using Fibonacci, it was 2 key power n. So how much it is less? Too much less, b go n, b go 2 key power n. Perfect. So that's it, thank you.